Okay, we're going to do another list induction problem. This time we're given a new function called rev, short for reverse. And here's how it's defined. Rev of the empty list is the empty list, R1. And rev of x cons xs, what it does is it takes the x, puts it in a list by itself, and puts it on the very far end, puts it on the far right hand side, and then concatenates it back onto rev xs by R2. And as a short note, a list containing just x, this is just shorthand for x cons onto the empty list. So this is just Haskell shorthand. So you can feel free to make this substitution wherever, and that's totally fine. We've also got some properties from previous questions. We already proved before that xs concat the empty list is xs by exercise 6 from the tutorial sheet. And we know for any three lists, if I concatenate all three of them together, doesn't matter if we do the first two first or if we do the last two first. And this is called associativity, or ASOC for short. So we want to prove for all list xs, for all list ys, the reversal of the list concatenated together is the reversal of the second, concatenate the reversal of the first. So which one do we induct over? Well, again, looking at the definition of concatenation, it's recursing over the first argument. So it looks like recursing over xs will get the job done. So we're going to prove by induction on xs. And this whole statement here will be my p of xs. Okay? So the base case is when xs is empty, i.e. I want to prove p of the empty list. There we go, p of the empty list, right? So we want to prove for all ys, reverse xs concat ys, for all ys, reverse of empty concat ys is reverse of ys concat reverse of empty. So we want to prove for arbitrary ys, rev of empty concat ys equals rev of ys concat rev of empty. Okay, so we'll start on the left hand side, which is rev of empty concat ys. Looking at the definition of concatenation, empty concat ys is ys. So this is just rev of ys by a1. And yep, that's fine. And now I have to somehow add this empty list onto the end. So we know rev of the empty list is empty. So it seems like the step before this last step will be rev of ys concat empty list. So here I can invoke the problem from exercise 6. So I can replace this rev ys concat empty. Because if I concat anything on the right hand side, it doesn't change it. That's by exercise 6. And I know the empty list is the same as rev of empty, so I can use the rule R1 backwards. So this is rev of ys concat rev of empty by R1, which is equal to the right hand side. Okay, so it's proven for the base case. Now we're going to prove for the step case. So for the step case, we're going to assume true for some list zs. So we're going to assume p of zs. What does that mean? We're going to assume for any ys, rev of zs concat ys is equal to rev of ys concat rev of zs. Okay, that's the thing we're going to assume. And now we want to prove for any new element z, the statement's still true if I put z on front of zs. So we want to prove for all z, p of z cons zs. So we want to prove for all z, for all ys, rev of z cons zs concat ys is equal to rev ys concat rev of z cons zs. Okay, so we're going to let z and ys be arbitrary. Okay, so we're going to start with the left-hand side over here for the step case. So the left-hand side is rev z cons zs concat ys. So what can I do from here? I can use the definition of concatenation to help me. I can always take the z out the front of the concatenation. This is equal to rev applied to z cons zs concat ys. And once again, I've forgotten to notate my inductive hypothesis, which is here. So this here is my assumption, which is denoted by IH for inductive hypothesis. So where were we? So I have rev z cons zs concat ys by rule A2. Okay. Now what can I do? Now I can use the definition of rev to help me. So if we have rev of some element concat onto a list, I take the element by itself and I move it all the way to the other side. This is going to be rev of zs concat ys concat list containing z by rule R2. Okay? At this point, this term here now looks like our inductive hypothesis, so we can replace it, being careful that this term is evaluated first. So we can replace this whole thing with rev ys concat rev zs concat list containing z. That's using the inductive hypothesis. Okay? So now what I want to do is I want to combine rev zs and the singleton list z. I want to combine these two terms together. But the problem is rev zs is trapped inside these brackets, right? I have to do this term first. Thankfully, I can use this property to move the brackets over. We can use the fact that concatenation is associative from a previous problem. So we can rewrite this as rev ys concat rev zs concat list containing z. But this time evaluating this term first using associativity. Okay? And the last step is to make this term here look like this term here, and I can do so by using the rule R2 backwards, because here we've got rev zs concat list containing z, so I can use R2 backwards to put the z on the front of the list. So this is going to be rev ys, leave that alone, concat, move the z onto the front by R2, rev z cons zs. What rule was that? That rule was R2, which is equal to the right hand side. Okay? It's true for the base case, it's true for the step case, therefore the statement is proven. Statement is proven for all list xs. So that means we've shown for all xs, p of xs. Which means we've shown for all xs, for all ys, the reversal of xs concat ys is the same as reversal of ys concat reversal of xs. And that's the proof.